Okay, so good morning, everyone. Let's do a recap of what we have done, about the special Korsrat rods. Very quick recap. So first, the kinematics. So we thought of a center line. So that was the center line of the rod, and we associated two variables with every point of the center line. That's little r of s and big R of s. So little r of s was to denote the center line of the deformed rod, and big R was to denote the average orientation of the cross section. Okay, so that's the kinematics. We also said that we extended this to the whole rod by saying little x of x1 comma x2 comma s is equal to little r of s plus big R of x alpha e alpha. Okay, so this was the constrained kinematics. So that's the constrained kinematic, you can say constrained kinematic extension to the whole rod. But we didn't really use this later on in our theoretical development. So, we haven't used that. So, I would like to emphasize that we haven't used that in our subsequent development. So, again we started with little r capital R kinematics, then we obtained balance laws. You remember you took a arbitrary segment of a rod and you did force balance and moment balance, and you obtained the two equations n prime plus n hat equal to 0, then m prime plus r prime cross n plus m hat is equal to 0. And while deriving these balance laws, you didn't use this kinematics, right? We never used this kinematics while deriving the balance laws. Once we had the balance laws, then we saw that we have more unknowns than equations. So that's where we started thinking about the constitutive model. So then we thought of constitutive law. And we postulated a strain energy per unit undeformed length of function, and we said that it must depend on the kinematics of our theory and is its first derivative. You remember we started with this, and then we used frame indifference, material frame indifference, or you could also say objectivity, to come up with this function, right? And then we said what are the physical meanings, of these two quantities V and K. V contains shear and axial stretch, and K contains bending curvature and twist, isn't it? So, V for example was big R transpose little r prime, and K was axial of big R transpose big R prime. Okay. And then, okay, maybe I could write here itself, we then related the derivatives of the strain energy with forces and moments, isn't it? And that again was done without resorting to this kinematics, isn't it? We wrote down the full energy of the rod, took the first variation, got the Euler-Lagrange equation, and compared that with this balance equation, and found out that your little n is equal to big R times del psi over del V, and little m is equal to big R times del psi over del K, right. And we also saw that del psi over del V have the shear forces and axial force, and del psi over del K have bending moments and twist. Okay. After this, we of course wrote down our balance equations, the 13 as a system of 13 first order ODE, isn't it? And then we talked about material symmetry in elastic rods, right. And we said, I mean, we derived that if the rod has got the SO2 symmetry, SO2, then it has the following invariants, and the energy must depend on those invariants. And the invariants were your V hat magnitude square, where V hat had only the first two components of V, V1, V2, right. I could also write it as V1 square plus V2 square. Then magnitude of K hat, which is K1 square plus K2 square. Then the dot product of V hat and K hat, which is V1 K1 plus V2 K2, and cross product of V hat and K hat, which was V1 K2 minus V2 K1 and V3 K3. So, these are the all invariants that you will have if the rod has SO2 symmetry. Okay, and then what we did? We did the Taylor expansion of this function in terms of V and K, and obtained the most general form of the quadratic energy, right. So, once you do Taylor expansion, then we obtain the quadratic form of strain energy, which was half of A times K1 square plus K2 square plus half of B times K3 square plus half of C times V1 square plus V2 square plus half of D times V3 minus 1 square plus half of E times V3 minus 1 into K3 plus half of, so this was without the half, plus F times V alpha K alpha, where alpha runs only from 1 to 2. Okay, so that is the quadratic term, and plus it also had the higher order term, which of course you can forget about if the strains are small enough. Okay. And these are the very interesting terms. This term denotes coupling between extension and twist, which says that if you stretch a rod, it is also going to twist, which is very intuitive. If you take a spring, for example, you stretch it, it is also going to unwind or overwind, it is also going to twist. So, it can, so this term models those coupling terms. And if you, for example, use O2 symmetry, if the rod is such that it has O2 symmetry, which means it has SO2 plus the reflection. For example, an isotropic rod, this would be for rods with intrinsic twist in them. Fiber enforced rods where fibers are helical, or we also thought of cables, intertwined cables, and there are so many cables, infinite number of cables intertwined with each other. So, they have SO2 symmetry. They do not have O2 symmetry because if you reflect, the right handed helix becomes left handed. But if the rod is such that it does not have that helicity in it, then it has O2 symmetry. You can reflect it and still the rod would be the same. So, for such rods, E and F are both 0. And you can recall that is what the expansion without E and F was the one that we used for our example, isn't it? So, that was the simplest example. So, anyway, you see, whatever we did here, we never resorted to this kinematics, isn't it? We never resorted to this kinematics all along. Okay, now, if you want to proceed further, then we ask, is our constitutive law complete? By that, do we have sufficient knowledge of constitutive model? So, of course, it is not, because the coefficients, for example, A, B, C, D, E, F, we do not know what it is. You can plug in some numbers, but if you want to get it for a real rod, for an aluminum rod or for any metallic rod having some cross section size, so that we still do not know how to get them, isn't it? So, how to obtain the coefficients? So, that is the question which we still do not know how to work out. And further, if the strains are large enough, if the strains V1, V2, V3, K1, K2, K3, if they are very large, this quadratic model is not sufficient. You also need to have higher order term. And in fact, why work with polynomial expansion? Why not with some other functional form? So, that is again something we do not know, isn't it? So, how to, you can say, what about material nonlinearity? So, these two questions are still unresolved till now. So, that is something we would like to solve, we would like to obtain. Okay. Okay, so do you have any idea how can we address those questions? If in doing the entire thing, we did not resort to that 3D kinematics or 3D elasticity. This was all done direct. But now perhaps it's the time to, go back to 3D elasticity. Otherwise, do you know any idea how to answer these questions? Of course, you can do experiment. You can take a beam, you can stretch it, you can bend it, you can twist it, and draw the force versus strain graph, for example, and look at the slope. That will give you those coefficients. But what about material nonlinearity? Experiments have those limitations. It can give you the initial slope very well, but the nonlinearity, how to get that? So, of course, experiment also has limitations. And besides, let's say I want to get it from theory, then how can we obtain it? So, any idea how can we talk about constitutive law? I mean, how can we get those constants? Yeah? Our goal is to get the strain energy per unit length for prescribed strains, isn't it? So, basically, if somebody tells you these are the strains, I would want to know what's the energy, isn't it? For any prescribed strains, I would like to know what's the energy. Now, by definition, what is this? This is strain energy per unit undeformed length. So, that is the energy of what? If you think of your rod, which has some V and K along its arc length. So, maybe over here it has V1 comma K1, and over there it has V2 comma K2. And if I say it has got psi 1 over here, so it has psi 1 over here and psi 2 over here, then that is the energy of which part of the rod? Psi 1 is the energy of which part of the rod? Yes?
DS element of the rod. Right?
DS element of the rod. So, what is that DS element? A small element here. What is that? Is that some point in the center line? Is that? So, that is actually the whole cross section, isn't it? It is not just the center line. So, you have to think of a cross section over here, and this psi is the energy of that cross section, isn't it? That is why when you integrate this psi with respect to length of the rod, you get the total energy of the rod, isn't it? So, this must be the energy of the cross section associated with a point over here, isn't it? So, this is the energy of the cross section. So, any idea how can you obtain the energy of this cross section? Maybe you think of it from 3D elasticity perspective. So, you have a rod, but you think of it as a 3D body. Okay? So, it is a deformed body, and here is a domain of that body, a small domain, and if somebody asks you what is the energy of that domain, what will be your answer?
principle of mechanics, like principle of virtual Earth, for example, and find a pair of strain and stress that will give that? Can we do this? I mean, of course, then maybe that's the wrong answer, because then we again rely on a material law to answer that question, don't we?
Yeah, I mean, you have to somehow rely on the material, of course.
Yeah, I don't exactly understand how the question is posed right now, because we are
Okay.
now trying to find at least the numeric values that make up the material law.
Okay. Okay. Let me repose the problem, or give you another picture of this psi. Psi of v comma k. What is that? Can we say that that's the energy of a small domain here, S1 to S2 integral over omega naught of S Can we write it? So, can we say that's your psi? See, this is energy per unit length. So, what we did is we took a small domain here, which was bounded by two cross sections, one at S1 and the other at S2. Of course, when the rod gets deformed, the cross sections are no more planar. So, it will become warped, does not matter. So, you can let it warp. But this energy, when you work out in the Lagrangian framework, then this is simply integration over the volume, undeformed volume of this part, and W. So, you have to integrate W over the undeformed volume of this domain, and this undeformed volume I have broken it into two parts. One is over the cross section and the other over the arc length. And then what is psi? That is the energy per unit length. Now, this domain, the length of that domain is S2 minus S1, isn't it? So, if you want per unit length, you divide by S2 minus S1, and then take the limit S2 tending to S1. So, you shrink the domain, and then what you have is just the cross section, isn't it? So, that is the cross sectional energy. So, this is same as, maybe I could extend this box. This is same as integration over the cross section of W of f d omega naught, right. So, if you are thinking of it as a 3D body, then if you want to get your psi, all that you have to do is get the deformation gradient, and you would know what is W. So, you have to assume that we know the 3D strain energy function, maybe isotropic, linearly isotropic, New Hookean, Muni-Rivlin, whatever. So, that is something we have to assume, or we have to think that it is known to us. So, that would be known, and then when you integrate this over the cross section, you get your psi. But you see, when you want to integrate this, you have to get your big F all over in the domain. So, now let me write down a different cross section here. So, you want to get your big F everywhere in the domain. So, how can you get that big F everywhere in the domain? As of now, we just said we have little r and capital R, and we do not want to resort to that kinematics also. Everything was working fine. But then we come here and now we are stuck. No, we can't get big F at every point in the rod unless we have some 3D deformation map, right? Only then when you take its gradient you get your big F. So now we have to get our deformation map, little f of x. Only when you know this that you can obtain, then you then take the gradient, obtain capital F, insert it over here, integrate over the cross section and get your psi. So, the question would be how to get this little f. Of course, you can solve it as a 3D elastic body, as a 3D, so you solve it as a 3D elasticity problem, then you get your little f. But that's something we want to avoid, right? We want to have a 1D theory of elasticity. So, you don't want to solve a 3D elasticity problem. So, maybe if you want to get exact big F, you have to solve 3D elasticity problem, but maybe you could work with some approximate big F, right? Maybe we have to think of some approximated big F. And one of the approximations is of course that constrained kinematics you see over there. That's one of the choice for us. So, that kinematics assumes that the cross section is rigid, it is neither shrinking nor undergoing warping. So, of course, if you use that kinematics and then get your big F, so that is of course one choice we have. So, that is going to be big R of S times, maybe I should work it out. So, the constrained one, if I use that, what will be big F? You take its gradient, you obtain little r of S prime tensor product E3 plus big R of S E alpha tensor product E alpha plus big R prime X alpha E alpha tensor product E3, and then you can take a big R common and you have big R transpose little r prime, which becomes V of S tensor product E3 plus E alpha tensor product E alpha plus K cross X alpha E alpha tensor product E3. So, of course, that is one choice. You can use that big F, plug in here and get your psi. See, this deformation gradient is only in terms of V and K, which is supplied to you from here. So, the question is, given V and K, what is psi? So, plug in that V and K here, get your deformation gradient, plug it here, integrate over the cross section and get your psi. Right. So, that is one choice with us, but what is the problem with this choice? This is constrained. So, is this going to give you higher energy or lower energy? No, it is a constrained deformation map. you are not letting the body relax completely, because you are saying that the cross sections are rigid. So, that means it is going to give you higher energy, right, and accordingly the stiffnesses also that you obtain will be stiffer. So, you will not get accurate result, but of course, you can use this kinematics. Many people use this kinematics to get their psi. We want to do better than that. So, what else can we do? Yeah. So, any idea what else can we do? Now, we have to somehow let the cross section relax, isn't it? But still not solve the 3D elasticity problem. You can let the cross section relax by solving the 3D elasticity problems. You solve the whole beam as a 3D body, but that defeats your purpose. So, what else can we do?
You can reintroduce the kinematic variable u, and there is an additive perturbation of how the local cross section is oriented.
Right. Yeah. So, that's something we had done in the beginning, isn't it?
Yeah.
Okay. All right. So, here is your cross section, and any point on the cross section here, little x, is simply your little r of s plus big R into x alpha E alpha, isn't it? If it is constrained, if you just put the cross section, but if you, because that is not going to give you a nice result, so we want to allow it to warp. So, maybe you can think of including some extra displacement to the cross section. To let it warp. And you have several choices to include that extra displacement. One is you solve 3D elasticity, then you get exact displacement. We don't want to do that. So, another choice could be, you see, this is our rod, which has different V and K all along, right. So, why don't I think of a different rod which has same V and K everywhere? Okay. See, our goal was to get psi for a given V and K, some V and K. Now, an actual rod, when it gets deformed, it won't have same V and K everywhere. So, what I am asking you, think of a rod which has same V and K everywhere. Over here it has V and K, here also it has got V and K, here also it has got V and K, every point has same V and K. And suppose that rod is allowed to relax completely. So, its cross section will be allowed to relax completely, subject to the constraint that it has same V and K everywhere. Okay? So, we are letting the cross section relax, we are letting it warp. Only constraint is that it has to have same V and K. Maybe I will. Okay. And then, so if I think of the deformation map here, what will the deformation map be? Your little x is equal to little r of s, whatever is the little r here, for having same v and k plus big R times x alpha E alpha. So, this part is the one with constrained cross section, but having same v and k, and then you add to it your extra warping of the cross section. Okay. So, but you see this extra warping that you have here won't be the same as the extra warping that you have over here. So, this u, maybe you can call it x star r star plus big R star plus u star for the star problem in which we have same v and k everywhere. So, this u star won't be the same as the u over here. Why not? Because in this configuration you have different v and k. So, this cross section, for example, is going to sense your the neighboring cross section, and it will see that, oh, it does not have the same v and k. So, it will try to deform slightly differently, isn't it? But this cross section here, when it sees its neighboring cross section, it sees it has the same v and k. So, certainly this will not deform the same way as this one. But if v and k are changing very slowly, the neighboring v and k is very close to what the v and k at this location is. So, if v and k are changing very slowly, then the u over there will be very close to the u star over here, isn't it? So, if v k are changing slowly, then u will be very close to u star. So, you see that is one recipe. What u should you use? Maybe we can use u star from this configuration, then get the deformation gradient and integrate over the cross section to get your psi, isn't it? Instead of using u, you can use u star because they are very close to each other. But then the question is how to get this u star. To get my u, I had to solve the full 3D elasticity problem for the entire beam. Can we get u star easily? That is the question. If we can get it easily, it would be nice, right? Now, you see what is happening here. Because the rod has got same v and k everywhere, so a cross section over here, for example, and a cross section over here, will they undergo same warping? Do you think so? Because it has same v and k everywhere. So, every cross section has got same v and k. Shouldn't they all undergo the same warping? Of course, they will have different orientation, but subject, if you forget about that orientation, then this extra u star won't it be same for every cross section? Because every cross section has got the same V and K. You know, it's a axially homogeneous problem. So the U star will be same. Okay. So what would that mean is that this U star is then only a function of big X1 and big X2. It's not a function of big X3 or S. Whereas over here, this U is a function of big X1, big X2 as well as your S. But this U star is not a function of S, but still it is very close to U because V and K are changing slowly. So what's the advantage now? I want to get this U star which is not a function of S. So if I want to obtain this U star, will we have some advantage? I mean, when you want to compute it, would you have to solve the problem over the entire domain of the rod? Because you see, every cross section is behaving in the same manner. So that means you can solve just one cross section. Instead of solving the whole rod, you solve only one cross section. So you are still solving the 3D elasticity problem to obtain your U star, but you are not solving it over the whole domain. You are only solving it in a cross section. So that's the advantage. Other way to look at this is, you see, what's the total energy of the rod? So the total energy is simply integration from 0 to L over omega naught of W of big F d omega naught ds. Now, what's your big F? Find out your big F, maybe big F star. So what's big F star? That's going to be little r star prime tensor product E3 plus big R star prime of x alpha E alpha plus U star of x1 x2 tensor product E3 plus R star E alpha tensor product E alpha plus del U star over del x alpha tensor product E alpha. That's your deformation gradient, which you could also write as, you take your R star common, and then this is R transpose, R star transpose into little r star prime tensor product E3 plus your big K star x alpha E alpha plus U star x1 x2 tensor product E3 plus E alpha tensor product E alpha plus del U star over del X alpha tensor product E alpha. Okay, the whole thing is within the bracket. So what I did is just took this R star as a common. And what's the advantage of this? You can now identify the terms. So it is big R star. What is R transpose R prime? That's your V, right? V is R transpose R prime. But V is constant in this particular case. Although big R is a function of S and little r is a function of S, but the strains V and K are not functions of S. So when you work this out, this gives you a V which is constant, V tensor product E3. Similarly, this K star, which is big R transpose big R prime, that also won't be a function of S because you have imposed constant V and K. So you get a K star, sorry, K cross X alpha E alpha plus U star of x1 x2 okay, I have to get some space. Plus whatever is over there, of course, plus E alpha tensor product E alpha plus del U star over del X alpha tensor product E alpha. Okay. Now you see in this deformation gradient, the thing inside the bracket is not function of arc length. They are only functions of x1 and x2. And the S dependence is over here in this big R star. So the S dependence is here, but the thing inside the bracket is independent of S. Okay. Now you have to plug in W F star here. So that's your F star. If I call the thing inside the bracket as, maybe I'll write over here, is big R star into F star, let's say tilde, the thing inside the bracket. And then you plug in this big F star over here. I've really messed it up. I don't have space to write, but I hope you are not confused. ds omega naught. And you see this F star is big R star into F tilde star. But the energy function is always frame indifferent. So W of F star will be same as W of F tilde star, isn't it? The energy function is always frame indifferent. So F tilde star. So you see there is no S dependence over here now. So this ds, sorry, so there is no S dependence. This thing can come out of the integral, and this simply becomes integration over the cross section of W F tilde star d omega naught times L total length. So you see what this is telling us is that the energy of every cross section is the same. So, total energy of the rod is same as length of the rod multiplied by the energy of one particular cross section. So, if you want to minimize the energy of the rod, then what should you do? You just minimize the energy of the cross section instead of minimizing the whole rod's energy. See, this was some mathematical proof, but you could have also seen it from physics, right? Every cross section is behaving the same way, so every cross section has the same energy. So, total energy is energy of one cross section times the length of the rod. So, you prove it mathematically also. Okay, thank you. So, that's missing here, tensor product E3. All right, so we have the recipe now. So, what is your psi of v comma k? That's nothing but you have to minimize the energy of the cross section for all possible u star. So, we have to minimize that energy w of f star. So, I minimize this for all possible warping, and the one that gives you the minimum energy would then be your psi. And you see this minimization problem, what is the domain of this problem? It is just one cross section. And here you have your f tilde, and f tilde is also, just for a remark, side remark, that is f tilde star is also the full f, but for s equal to 0. Because when you plug in s equal to 0, this rotation will vanish. Okay, so anyway, so we have to, so that's the problem that we have to work out. So we only solve one cross section, a cross section problem. Okay. Now, do we have to be careful about some anything when we do this minimization? Just look at this problem here. This u is on top of the constraint map. So, if this u is not there, your cross section is here, it is just a rigid cross section. Sorry. Now, when you work out the minimization, when you do this minimization, it is possible that you get such an u which changes the centroid of the cross section. Is it possible? Isn't it? I mean, you can have a u which brings this cross section from here to here, right? Or you can have an u which changes the orientation of the cross section. If it is like this, it changes to this. So, you want to avoid that, because if it changes as little r and capital R, then the strain in the rod will also change. So, that is something you do not want to do. For example, you see, suppose your little r does not change, but the u is such that the rotation average orientation has changed. Then what is your v? V is big R transpose little r prime. So, little r did not change, but if u is such that its average orientation changes, then v also change. So, the strain has changed. So, that is something you want to avoid. So, this minimization therefore has to be done under some constraints on this u star. Okay. So, this has to be done under some constraints. All right, I hope I am not confusing you guys. No? Okay, very good. All right. So, we are now going to talk about how to work out this minimization. So, that is our next thing. I hope this is understood. So, the whole idea is that we want to introduce that extra warping u star. Instead of introducing u, which is more exact, but then you have to solve the 3D elasticity problem over the entire beam. So, instead of solving for u, I want to be done with just getting u star, because getting u star is easier and it is also close to u. So, the solution that you will get will be very close to the exact solution. Without this u star, of course, you can do that also. So, putting u star equal to 0, but then you get more inaccurate answer, right. Okay, so, the whole thing is, so we will now talk about how to get that u star. All right. So, once you get your u star, you can get your energy function, and that is it about the constitutive law, is not it. All right. So, again, so we are going to solve the star problem, which has same v and k everywhere. So, it has uniform v and k. So, our first goal would be to obtain the configuration of the rod. When the rod is subjected to uniform v and k, how does the configuration look like? What is your little r and what is your capital R for uniform v comma k? All right. So, to get that, we all know that big R transpose big R prime is equal to your big K. The right hand side big K is a constant, is not it? But on the left hand side your big R would change with arc length, but they have to change in such a way that this gives you a constant K, because I am imposing constant K here. So, you bring this big R transpose on the other hand, on the other side, and then you get big R prime is equal to big R times K. And what will be the solution to this problem? This is very much like x prime equal to k times x. What is the solution to that problem? X prime equal to kx. Then you do separation of variables, dx by x is equal to k times dt, then integrate on both the sides. What do you get? Exponential function, right? Maybe I should write here. If you are solving this x prime equal to kx, that means dx by x is equal to k times ds, and then you integrate, you get ln of x is equal to ks plus some constant c, which means x is equal to another some constant c naught times e to the power ks, right? And you see this problem is very much like that problem. Here your little x is the unknown, here big R is the unknown. You have prime over big R is equal to the constant k multiplied with the unknown big R. So you can take the idea from here, and when you work out the mathematics, you get the same solution, a similar solution, that your big R of S will be equal to some big R naught into exponential of k times S. Okay. This big K is a skew symmetric matrix, and when you work out its exponent, you get a SO3, and this big R naught is a constant of integration. When you evaluate this at S equal to 0, you see what you get. R naught into exponential of k times 0. So, exponential of 0 is identity. So, big R at 0 is equal to big R naught. So, that is how you get your constant. So, this big R naught is the orientation of the cross section at S equal to 0. Okay. That is the orientation of the cross section at S equal to 0. Now, you see you had this rod which was subjected to same V and K, and we want to get little r and capital R. Won't we be fine if we get a configuration which is a rigid rotation of this one, because you just want to get how it is deformed. I mean, can we set this big R not equal to identity? It won't really do any harm if we set big R naught equal to identity, isn't it? It will be just like rotating the whole rod rigidly by big R naught. Okay. So we are just going to do that. So, set big R naught equal to identity. See, because we are prescribing strain here, we are not prescribing displacements. When you prescribe strain only in a problem, you always have that non-uniqueness of solution. You can always rigidly displace your any solution and you have the same strain, isn't it? If you are only prescribing a strain, then you have infinite solutions. You have one solution, you rigidly displace it, you get another solution. So, that is what is happening here, because we only want to we have only prescribed V and K. So, there are so many solutions. You can have any R naught, still the rod will have same K. For any R naught, the rod will have same curvature. So, why do not we just set R naught equal to identity to just get one of those solutions. Okay. So, that is your, so set this equal to identity. So, your big R s is equal to exponential of K s. All right, very good. Then how to get your little r then? Little r of prime is nothing but big R of S times V, isn't it? So, now substitute your big R from here, So, that is your little r prime is equal to exponential of K s times V. So, what is your little r then? Some constant little r naught plus integration from 0 to s of exponential of K L d L times V, isn't it? And again, what is the meaning of little r naught? You substitute s equal to 0, this integration vanishes, you get r naught. So, little r naught is the center line position of S equal to 0 cross section, which you can set to be again 0, right. So, it is like just displacing the whole rod. So, we are going to set that equal to 0. Okay, so, we are doing some mathematics, but you will see the final result will be very exciting. So, your V and K are prescribed, right. So, suppose you have some V and K, vector V, vector K, and the angle between them is phi. Okay. So, think of two directions, one along K, a unit vector along K, and I call it as K hat, and another unit vector in the plane of V and K, but perpendicular to K hat. So, I will call it K perpendicular, and of course, it is hat unit vector K hat perp. Okay. And then I want to write my V in terms of K hat and K hat perp. I want to decompose this V. So, what will V look like? So, V is then going to be cosine of phi times K hat plus sine of phi times K hat perp, and of course, we have to also multiply by the magnitude of V times the magnitude of V. Okay. And let us substitute this in that formula over there. So, what do we get? So, little r of S is then 0 to S exponential of K L times this formula. So, which is your V comes outside times cosine of phi of K hat plus 0 to S exponential of K L times sine of phi times k hat perp. Right? Now we can do a little more adjustment. This is same as magnitude of v. See, cosine of phi is a constant. Phi or your phi does not depend on L, so it can come out of the integration. So this is simply cosine of phi 0 to s exponential of k L times k hat d L plus sine of phi times 0 to s into exponential of k L times k hat perp d L. Right? Now look at the first term. What is this going to give you? Exponential of k L. What's the axis of this rotation matrix? It is definitely a rotation matrix. And what's the axis of this rotation matrix? It's nothing but the axial vector of k, which is same as your little k. So that's going to point along k hat, right? So the axis of this rotation matrix is same as k hat. So your k hat is also the axis of the rotation matrix. So this rotation matrix times the axis of the matrix, what will that give you? Rotation times the axis, what does that give you? The axis itself, right? The rotation does not do anything to its axis. So this times k hat is same as k hat, and then this k hat is then independent of L. It comes out of the integral. See, right now you could not take it out of the integral because exponential of k L, so L is there, but multiplication of these two is just k hat, comes out of the integral dl 0 to s. What is that? Just s. So this term is s times cosine of phi times k hat, and then you have this term plus sine of phi 0 to s exponential of k L into k hat perp d L. Okay. So, see, what is this doing? This term is simply translation along k hat. So, if you think of a configuration with k hat pointing in this direction, let us suppose k hat, then this term, as you change your little s, you are propagating along k hat. So, you move along k hat as your little s changes. But what is this term doing? Can you see what is this? So, you have a rotation matrix multiplied with k hat perp. So, that is the rotation matrix, and k hat perp is in that direction. So, what is that going to give you? So, exponential of KL times K hat perp. So, think of, suppose now I am giving you a different view. Suppose your K hat is coming outside. Okay, over here K hat is in this direction, but now think that K hat is coming outside. Okay, so that's your K hat. So K hat perp, since it is coming outside, it will be in the plane of the board, isn't it? Maybe let's say somewhere over here. That's your K hat perp. And what will be exponential of KL times K hat perp? So it's simply rotating this vector about this axis, right? And what's the magnitude of rotation? It's simply the magnitude of the little k into L. So the magnitude of rotation is the magnitude of k times L, isn't it? So for a given L, then this, if this is your k into L, then your K hat perp will just come here. The rotated K hat perp, which is exponential of K L into K hat perp, right? So you see, the whole objective of this matrix is to rotate it, and then you want to integrate that rotated vector. So this rotated vector you are integrating. What will you get? Any idea what will you get? Okay, just look at this term. Suppose this is z prime. Z prime equals 0 to s. Sorry, z. This is z. Z equal to 0 to s exponential of kl times k hat perp dl. Then what is z prime? So this is z of s. Z prime is simply exponential of kl into ks into k hat perp. So this is going to give you a curve z such that its tangent is this, right? The tangent to the curve is this. Now the tangent to the curve is just rotating. The magnitude of the tangent is constant, but it is rotating. So what will you get when you integrate that? Think of a circle. So this is the curve of the circle. That's the tangent. Everywhere tangent is rotating. When you integrate the tangent, what do you get? The circle itself, right? So, in case of a circle, in case of a curve which is a circle, the tangent of the circle is also rotating, and when you integrate the tangent, you get the circle. Right? So, now you think, what is this term doing then? This term is going to trace a curve which will be a circle, and the normal to that circle will be k hat, because the tangent is k hat perp. So, the plane of the circle will be the plane of k hat perp and the rotated k hat perp, and the normal to the circle will be k hat. So, this term generates a circle whose normal is along k hat, whereas this term that you see over here generates a straight line along k hat. And what do you get when you have both the terms together? So, you have a curve which is rotating about k hat and also moving. So, you see, if it is just rotating, it is like this, if it is just translating, it is like this, and if it is doing both, right. So, what do you get? Helix, right. So, that is the helix. So, that is what I said, it's you will get something exciting. Okay. So, you can actually integrate this, and then the formula that you get is I am just going to write here little r of s is equal to magnitude of v times cosine of phi s k hat plus sine of phi over magnitude of k into identity minus e to the power s k of k hat cross k hat perp. Okay, so this is basically the equation of the circle that I was talking about, and that is the straight line along k hat. So, this is straight line and this is circle. You can also define is some new quantities tau, which is v cos phi, and xf, which is sin phi of k hat cross k hat perp divided by k, which is actually same as v cross k divided by norm of k square. Okay, so we get a quantity tau, we define tau and xf, and then you can write your little r of S equal to S tau k hat plus identity minus exponential of s k e to the power s k into x f. We're just writing the same thing in a different form, and that's how helix is usually written. So this term is for translation along the axis of the helix, and this is for rotation about the axis of the helix. Okay. And this tau is related to pitch of the helix, and the magnitude of x k x f is related to the radius of the helix. Okay. So, am I done with time? It looks like I am done. Okay, so we'll proceed from here in the next class.